7.2 lesson. Now, we had a bit of a discussion in 6.3 about the standard conditions in delta G versus K. And I think the easiest place to start is at equilibrium. If we know that delta G standard is 0, then we are at equilibrium. Now, we also said that the standard conditions are when Q equals 1. When you do the K math and you get 1, you're at standard conditions. Q is 1 at standard conditions. Now, if you're lucky enough, so to speak, that your standard conditions are also at equilibrium, well, then K also equals 1, because the definition of equilibrium is that Q, your current conditions, are equal to K. You might need to stop and pause and write this stuff out, but it does work. At equilibrium, Q, your current conditions, must equal K. But at standard conditions, Q equals 1. So both Q and K are equal, and they both are equal to 1 if the standard conditions are such that you are at equilibrium. Now, at equilibrium, nothing much is happening overall. The reaction is flowing equally left and right, and so it does stand to reason that the voltage potential of the cell, of the voltaic cell we're discussing, is 0. It neither really wants to pass electrons to the left or to the right. So the potential for electron flow is 0 at equilibrium. And we said in 7.1, if the reaction wants to go forward, then the standard cell potential is positive. And we know that when reactions want to go forward, delta G is negative. And we said in standard conditions, if it wants to go forward, then K must be greater than whatever it was at equilibrium. So it must be greater than 1. If it's in reverse, then all that logic reverses. Delta G is a positive number. K is less than whatever it was at equilibrium. So K is less than 1. And the standard potential of the galvanic cell we're talking about must have a voltage potential that's negative, because that would be pushing the reaction in reverse. And so delta G and standard cell potential have opposite signs. However, they are proportional. If one doubles, the other doubles, except the signs are reversed. Now, we had a bit of a discussion also that delta G is in joules or kilojoules per mole. Really, it really should say per mole. And standard cell potential, or E standard, or E naught, is in volts, and a volt is a joule per coulomb. Hidden inside every capital V volt is a joule divided by a coulomb. And again, a coulomb is just a large number of electrons that makes it very convenient when we're talking about electrical things like volts and amps. You don't even have to know the number. Like if you don't remember what a mole is, it usually doesn't ever come up. But we can convert between coulombs of electrons and moles of electrons using Faraday's constant, this conversion factor here. So delta G standard is proportional to the standard cell potential. Of course, the signs are different. And let's get a little bit more conceptual about that. The energy released is proportional to the push on the electrons. If the push on the electrons, remember that's what volts is the energy per group of electrons. If that doubles, then the free energy of the electrochemical cell is doubled. Now, I know the signs are reversed, right? It's more like we would probably think of it as negative is proportional to the positive. But the signs are opposite. But if you get double the push on your electrons, double the energy per group, you get double the free energy of the total reaction. And this is just a different way of writing the same thing, because really you've just converted to joules per mole of electrons, but it's still energy per group of electrons. See, the coulombs cancel out here, and you end up with joules per mole of electrons. And so it's still saying that it's proportional to the energy per group of electrons. And this is also saying that the free energy is proportional to the energy per electron, per group of electrons, but then it matters how many electrons each reaction gives. Notice this is just proportional, but this is equal to. So the total free energy will be the energy given out per group of electrons, and here we convert it to moles as the group because the coulombs will cancel out, times how many electrons did this reaction give. If one reaction gives 2 electrons at the same rating as a reaction that gives 1 electron, then the overall free energy per mole of reactions is double. If a reaction has the same voltage rating but gives 3 electrons each, then it would be multiplied by 3 for the total free energy created by the system. So delta G depends on the moles of electrons, but E naught does not use it because, again, this is in volts, and volts is energy per group, not the number of groups. It's energy per group. In the same way that a molar mass is a mass per group, it doesn't rate it for how many groups you have. It's defined as per one group. So the volts is energy per one group of electrons called a coulomb. So then at the standard state, your standard delta G would use the number of electrons, Faraday's constant to convert to moles, and the standard cell potential. Or we could do it at whatever state you happen to have, not the standard state, because I mean, who's working at the standard state most of the time in real life? Almost no one, right? So whatever conditions you've got, the current voltage that you're currently experiencing, and we'll get into how to find that, converted to moles instead of coulombs of electrons times how many electrons it's giving, will give you the free energy that that cell can give you right now and not at the standard state. So, skipping the part about deriving the Nernst equation, there was a Dr. Nernst, of course. Where else would they get a name like that? We arrive at this equation, which is in the reference pages of the test. You'll notice it looks a lot like the delta G standard equation that relates to K. So what we have here is the voltage you're currently experiencing in the conditions you just currently have that aren't standard. That's the standard conditions voltage, the standard cell potential. Here's that R value we've seen so many times. Remember to use the one with joules in it. The Kelvin temperature. This is going to convert your moles of electrons to coulombs, because remember, voltage is rated in coulombs, joules per coulomb. And the natural log of your K math in your current conditions. So capital Q. This can be rewritten to involve K, though. If you were at equilibrium, the cell potential at equilibrium is 0 because no exchange of electrons is taking place. So this is a 0, so we can pull this over. They both become negative on both sides, so let's just call them both positive. And at equilibrium, Q is K. That's the definition of equilibrium. If you're at equilibrium, your current conditions are such that K is true. And you do still need this version. So you need to be able to look at this one and say, oh, yes, it's really that. And you don't get to walk in with notes. So you need to be able to remember that at equilibrium, this is going to be 0, this moves, and Q is always K at equilibrium. So here's a graphic organizer, as some people would mention it, about where to use these equations. Now, personally, I think it's a little obvious, and I don't know how much this is needed, because we know that to convert between K and delta G, we would need an equation with K and delta G in it. And to convert between cell potential and K, we would need a formula with cell potential and K in it. But I would get really familiar with these. Also, I'd like to go back and point out that this formula is in a test, and they expect you to know that if you're not at standard conditions, it just turns into this one, and that's going to come up. So this is a repeat, but we have this zinc and copper galvanic cell again. And again, we would flip the standard reduction reaction of zinc so that it's oxidizing, and we know that because we know that nature will run the reaction that produces a positive voltage, and one of these has got to flip. They can't both be receiving electrons. Something has to give it, and if I flip this one end to end, it make it oxidize. I'll get a positive value here, and when I add these together, I'll now get a total positive voltage. So it must be this one giving the electrons, and so the electrons are doing this, coming out of the zinc and going into the copper. So what's the delta G standard for this? Well, using the reaction that I mentioned on the other side, the number of electrons being passed is 2 per mole. Because remember, delta G is rated in kilojoules per mole of reaction. And if we do a mole of this reaction, 2 electrons get passed each time. So it's 2 moles of electrons passed every time. Now, the E standard is rated in coulombs. Remember, a volt is a joule per coulomb. So this is that. A volt is a joule per coulomb. And so I need to convert out the coulombs and put in moles because delta G is in kilojoules per mole of reactions. So when I use 2 moles of electrons, I'm using 1 mole of reaction, and Faraday's constant here will convert out of coulombs and into moles because the moles of electrons will cancel here. Also on the test, they don't round off the coulombs here. They write it like that in case that helps you recognize it. But of course, you get a calculator for this kind of a problem anyway. So they're not going to write that kind of thing into a multiple choice. So this cancels out that, this cancels out that, and we get joules per mole of a reaction when we multiply through. Also, don't forget that it's negative because a positive voltage will give an outward energy out of the chemical reactions. Energy is leaving the reactions. It's powering, say, the light bulb here kind of thing. So energy is being produced by the reaction, and therefore energy is going out of it. So the sign on delta G is negative. So this needs to be a positive for the reaction to be favored. But remember, favored reactions have negative delta G's. So this reaction has a negative slapped on it so that we'll get a negative value for delta G standard in the end. Let's go back to the Nernst equation for a moment and solve it for K. So at K, I know I must be at equilibrium, and we said that E non-standard disappears. But if we solve it for K, this whole piece divides under, and then I have to take e to the power of both sides. So this over that becomes the exponent on e. And when I do e to the power of natural log, they unzip and disappear. And so I get k is equal to what I said before, small e to the power of E standard times N times F over RT. So we're going to take all that stuff we learned and put it in here. The voltage of E standard, the number of moles of electrons, Faraday's constant to convert it to coulombs so that it matches the units inside volts. Remember to get the R value that has joules in it because we need to cancel the joules out of the E standard part. Remember that there's joules in there inside volts, and the Kelvin temperature. All this divided by all that gives a value, and then we take inverse natural log and we get a K value, which in this case is very large. Now I would jot this down. We have already said that the standard state for delta G and so forth is where Q equals 1. And that's still true here, but what that means for the galvanic cells is that the molarities will both be 1, or they will produce a Q that is 1. So it's easy to think of them as having both molarity of 1 so that we get 1 molarity over 1 molarity and we get Q equals 1. That's for the standard state. But what if you're not at the standard state? What if zinc is 0.1 molarity and copper is 0.5? How does the voltage change? Let's use those molarities and find Q. We get 0.2. Now, the other thing that I found difficult was to remember which one to put on top because this is on the right, I started thinking of it as the product. But if you look at the overall reaction, the zinc aqueous is the product. This is the product and that is the reactant. And so it's zinc over copper. Products over reactants to the power of the number in front. And the coefficient for both of these is 1. So we just end up with zinc molarity divided by copper molarity, and we get 0.2. Well, we just found that K is this enormous stinking number up here, so Q is decidedly less than K. When Q is less than K, we don't have enough numerator. We need to create more product, and we need to create a lot more product if we're going to reach that number. Nature very much wants this reaction to happen. So this reaction is favored toward the forward direction, and then delta G would be less than delta G standard. It's left with the standard state. Standard state would be Q equals 1. Now this gets a little hairy, so let's pay attention. Remember how Q was 0.2 in our current circumstances? But in the standard conditions, Q is 1. So in standard conditions, Q is 1, but our Q went down from there. If Q goes down, this whole term gets smaller, and I subtract out a smaller number than at standard conditions, so I get a bigger answer. And E not standard, current conditions, is bigger than E standard conditions. If E got bigger, then what about delta G? If E from standard got bigger for non-standard, then this whole set on the right got bigger, which with that negative sign means it's more negative. So delta G changed to be more negative from the standard conditions to the ones we just dealt with. And delta G is less than or more negative is another way to say it than delta G standard. So what are the values of E and delta G? And we have equations, so we already know Q, we know Kelvin temperature, we know R is given to us, and we know delta G standard because we found it up here. Put them all in, and you should get negative 216 kilojoules per mole. What is E? Well, we know E standard because we found it at the top. We just found Q. We know R from the reference table. We know Kelvin temperature. We know Faraday's constant to convert into coulombs. And we know the moles of electrons. Now, in this case, remember, we're going to get a rating for E. So our unit is going to be in volts. So make sure that you're converting out of moles and into coulombs. Coulombs goes on top here so that we get joules per coulomb. We're not canceling the coulombs, we're canceling the moles of electrons.